Hi everyone, today we're on page 11 and we're looking at gas volume calculations and mainly focusing on this idea of molar gas volume. Now this is something that we haven't seen before, but it takes a few of the ideas that we've used both here and in Unit 1 in our calculations and puts them together so that we could calculate the gas volume for any gas in an equation that we're given. Now, you should be very aware and knowledgeable about the fact that a gas has particles which are not close together. They're very far apart. They have the ability to move freely because of the lack of intermolecular forces between them. And so that allows them to have very different properties to solids and liquids, especially when it comes to volume. You already know that a gas will fill the volume of its container. But the thing we're focusing on first of all today is the fact that the volume of a fixed mass of gas is very dependent on temperature and pressure. And we're thinking about this in two examples that are coming up. Here you can see in the balloons, well really it's the one balloon, that there are 6 gas particles in it. So we're assuming that there's a mass of 6 grams. Okay, let's just assume that. You can see that in the ice cold water, the volume of the gas is very small compared to when we heat it up by putting it in the boiling water and the volume increases. So we can make this statement that it says here, if the temperature is increased, then the volume of the gas is increased. And let's think about that. When we add heat to any particles, what will happen is they will gain energy and they will move around more. It's really obvious with gases. With solids and with liquids, we see expansion because the particles only have space to vibrate. But because the gas is able to move around and fill the space, they can dramatically move around. And so we can see a massive increase in the volume. So increasing the temperature can increase the volume of gas, even though its mass hasn't increased. When we're thinking about pressure here, we can see on the left-hand side of the image, it's a very low pressure. Now, if you sit there and count the number of particles that you have, you will see that you have got 15 particles on the left, and you should then have 15 on the right. So the mass and the number of particles here hasn't changed, but our volume has, because when we add pressure, we squash these particles into a smaller space. Because they were originally spread out, then they can move closer together and we can decrease our volume. So if we increase pressure, then the volume of a gas decreases. And all these properties of gases are really important for us to keep in the back of our minds as we do this topic. Here in this image, you can see we put the idea of temperature and pressure together, and it says here all balloons contain 1 mole of gas. So they all contain 6.02 times 10 to the 23 molecules. So the same number of molecules in each balloon. For balloon A, we've got a medium temperature and a medium pressure. Balloon B, we've got a high temperature and a low pressure. Those are the conditions that a gas loves to have to increase its volume. And then C, the temperature's low, so the particles aren't moving around that much, and the pressure's high, so they don't have space to move around, so we can see a low volume. So this is how we can apply our knowledge to specific situations and see how the volume would differ. Today we're really focusing on this idea of molar gas volume. And what we have to do first on page 11 is we've got to write what the molar gas volume is. And the shortened way of doing that is a capital V, small m for molar gas volume. And this is your definition. The molar gas volume is the volume of 1 mole of gas under specified conditions of temperature and pressure. So it's the volume of 1 mole of gas, the volume of 6.02 times 10 to the 23 particles of gas. If you've that many molecules of gas under specific conditions, such as temperature and pressure, that will be your molar gas volume. So write down that definition now. In that same space, I want you to write this down. This is our most common. At room temperature and pressure, the molar volume of any gas is 24 decimeters cubed. So at 20 degrees Celsius and 1 atmosphere pressure, which is how the room is, then the volume of 1 mole of any gas will be 24 decimeters cubed. So 6.02 times 10 to the 23 molecules of any gas, your molar gas volume will be 24 decimeters cubed. So we can make this statement that at room temperature, Vm equals 24 decimeters cubed. Now, in the box below, it's a shaded box, so it's quite difficult to see. What I want you to write in there is this equation to calculate Vm, or molar gas volume. So Vm equals the gas volume divided by the number of moles. So if you ever were asked to calculate the molar gas volume, then this is the equation you would use. Now, if you're asked what is the molar gas volume at standard room conditions, or at 20 degrees and 1 atmosphere, then you would say 24. But say they give you different conditions, this is the equation you would use to write that out and to work that out. Of course, if you were simply asked to calculate the mass of a gas, that's something different. So you would still use mass equals moles divided by RMM or MR. Okay, so mass equals moles divided by MR or RMM. That is what you would do for mass. Now, just below where you've written that equation, you'll see there's a box and it's already written for you. So if you want to calculate gas volume, then what you'll do is you'll take the number of moles and you'll multiply that by Vm, the molar gas volume. Okay, so if you were asked to calculate the gas volume at room temperature, you would take the number of moles of whatever you're looking at and multiply it by 24 decimeters cubed. We can rearrange this equation again, and I want you to write this in at the bottom of page 11. So then if you're asked to calculate the number of moles, then you would take the volume of the gas and you would divide that by molar gas volume. So again, if that was at room temperature and 1 atmosphere pressure, so standard conditions, then what you would do is you would take your gas volume and divide that by 24, and that would give you your number of moles. And then you could go on from there and do other calculations then once you've calculated your moles. Turn over to page 12 then, we're moving on, and we're looking at this man, Gay-Lussac, okay? And Gay-Lussac stated that the volumes of the reacting gases and the gaseous products in an equation or a reaction are in ratio to each other if they're measured at the same temperature and pressure. And I mean, when it comes to experiments, normally that's what happens. We have the same temperature and pressure in the room throughout the time of doing the experiment. So then all of these different chemicals are in ratio to each other as their gases. Now the example we're using here is methane plus 2 oxygens will produce carbon dioxide and 2 water vapors. Look at your state symbols there. They're all gases, okay? So what we could be given here is we could be given the volume of one of these gases, and then using the ratios that we have with our molecule numbers, which come in front of the molecule, then we could work out the ratio and work out the remaining volumes, just like you would when we're calculating reacting masses, when you're asked how much of this solid will be produced when you start with this amount. Okay, so we've done that before. This is very similar. So we're told in this example, if 10 centimeters cubed of methane reacts, look at the reacting ratios to work out the other volumes. Well, look at the ratio of methane to oxygen. There's an imaginary 1 in front of methane, so the ratio is 1 to 2. So if we've 10 centimeters cubed of methane, then we should have 20 centimeters cubed of oxygen. So write that down. Then we look at carbon dioxide and we go back to methane. We always start with methane because that's the volume we were given. So look at the ratio between methane and carbon dioxide. It's 1 to 1. So therefore, if we have 10 centimeters cubed of methane, we have 10 centimeters cubed of carbon dioxide. And then finally looking at water vapor, back to methane, there's a 1 to 2 ratio between methane and water vapor. If we've 10 centimeters cubed of methane, then we have 20 centimeters cubed of water vapor. And often it's just as simple as that. Let's look at example 1. Example 1 says, calculate the volume of carbon dioxide produced when 25 centimeters cubed of propane gas are burnt completely in 20 centimeters cubed, which is an excess of oxygen. Calculate the volume of oxygen remaining at the end of the experiment. So we know we start with 25 centimeters cubed of propane, and we know we have more than enough oxygen. So oxygen here, remember, because it's an excess, is not specific enough. So it's not the limiting reagent. Propane will be the limiting reagent, and so it will dictate the ratios here. Now, in the next slide, what we're going to do is we're going to break up how we would answer this question very simply. Your first step when you go to do any of these equations is to make sure you've got a balanced equation written out. That is your responsibility to look for. So if it's not given to you in the question, make sure you do that, or else you're wasting your time. Thankfully here it's been written for us and it's balanced. So the first step for us to do is to write the volumes we know underneath. So we've been told that we have 25 centimeters cubed of propane. There were originally 200 centimeters cubed of oxygen added. But look at the green box here. We were also told it was an excess. And excess means there's more there than has reacted. So here 200 was put in, but not 200 was used. So we've got to use the 25 centimeters cubed of propane as the limiting factor. It's the one we're using. In the question, we've been asked to calculate the volume of carbon dioxide produced, and then to calculate the volume of oxygen left. So the first thing we want to do is look at the carbon dioxide. That's what we were asked for first. Remember, we do this with our ratio. So the ratio of propane to carbon dioxide is 1 to 3. If 1 is 25 centimeters cubed, 3 is 3 times that. So 3 times 25, the volume of carbon dioxide then produced is 75 centimeters cubed. So that's the first part done. The second part then is looking at oxygen. What we are going to do with our ratio is we are going to find out how much oxygen actually was used. So here the ratio is 1 to 5. So we take 25 and multiply it by 5. And that lets us know that 125 centimeters cubed was used in the reaction. We have to do an extra calculation there to find out how much was left at the end. And remember, what was left at the end was the amount that wasn't used. So 200 take away 125 gives us 75 centimeters cubed. So 75 centimeters cubed of oxygen was left at the end. It wasn't used up in the reaction. It was the excess amount then. So we found out here that we started with 25 centimeters cubed of propane. We started with 125 centimeters cubed of oxygen. We produced 75 centimeters cubed of carbon dioxide, and 75 centimeters cubed of oxygen was left at the end from that 200. So it's not too hard. If you are still struggling with this, you can look up a few videos on YouTube, or you can get in touch with me. Example 2 is a slightly trickier style of question, yet it's very common in the exams, and once you've mastered it, they're all pretty much the same. So it says 20 centimeters cubed of an unknown gaseous hydrocarbon CXHY were mixed with 80 centimeters cubed of excess oxygen in a graduated tube. A spark was applied and the resulting mixture of gases allowed to cool to room temperature. 60 centimeters cubed of gas remained. When this gas was exposed to sodium hydroxide solution, the volume reduced to 40 centimeters cubed. Determine the formula of the hydrocarbon. The first step that you're told to do in your notes here is write a general equation for the combustion of a hydrocarbon. What we have here on the screen is that general equation. And for this style of question, this will always be the general equation. So you can just learn this off. Okay? So here it is, CXHY plus X plus Y over 4 O2 produces X CO2 plus Y over 2 H2O. Now on your notes, it says a few points to note. There is an excess of O2, so all the hydrocarbon is used. The final mixture will consist of CO2 and unused O2 as the water vapour condenses, and only acidic gases will react with NaOH. On the next slide, I'm going to show you where you pick this out of this question. What I've done here is I've summarised the main information that we've been given here. So we've been told that we start with 20 centimetres cubed of an unknown gaseous hydrocarbon. We've been told 80 centimetres cubed of oxygen has been added into this mixture. However, that's more than we need. So from there, we realise there will be oxygen left over at the end. Then we're told it will cool to room temperature. When you're told it will cool to room temperature, you want to look down at what's been produced and see, does any of that change state at room temperature? Hopefully you notice that water won't be a gas at room temperature. It will have changed and it will have condensed back to a liquid. So it won't be in your final gaseous mixture at the end. We're told 60 centimetres cubed of gas remained. Water won't be a part of that. What you will have in that is you will have the carbon dioxide that's being produced and the leftover oxygen. We're told when this gas was exposed to sodium hydroxide solution, the volume reduced to 40. It went from 60 to 40. Well, when you react an acid with an alkali, there's a neutralization reaction. So what has happened is whatever was acidic in that gaseous mixture has reacted with sodium hydroxide and has been neutralized, and so is no longer part of the gaseous mixture. So you want to look at oxygen and carbon dioxide and decide which one's acidic. Hopefully you've realized it's carbon dioxide. And then at the end, you're determining the formula of the hydrocarbon. So looking at these steps then, 20 centimetres cubed of an unknown gaseous hydrocarbon CXHY. We know we've got 20 centimetres cubed of CXHY. We also know that we've been given 80 centimetres cubed of excess oxygen. So we do have 80 centimetres cubed of excess oxygen. It's not a value we can use to work out our ratios. Cool to room temperature, water condenses, so it's not part of the final volume. This here is going to be our final volume, the leftover oxygen and the carbon dioxide produced. We know that there's 60 centimetres cubed of gas remaining, so them together will produce 60 centimetres cubed. When this gas was exposed to sodium hydroxide solution, the volume reduced to 40 centimetres cubed. Carbon dioxide is acidic, so reacts with the sodium hydroxide. So, from that mixture of 60 centimetres cubed, how much of it was carbon dioxide? Well, if the carbon dioxide reacted with the alkali, then 20 centimetres cubed was. Don't mind my dog there, she's just whinging at me. Now that means then the amount of oxygen left at the end was 40 centimetres cubed. If we initially added 80 and 40 was left, then 40 must have been used up. So let's look at these now. Look at the ratio between CXHY and CO2. It's 1 to 1, okay? Because we 20 centimetres cubed of our hydrocarbon and 20 centimetres cubed of carbon dioxide produced. So X must equal 1. It's a 1 to 1 ratio. So then you can start to put the number 1 into this instead of X. So our ratio is going to be 1 to 2 to 1. So X will equal 1, and then X plus Y over 4 will equal 2. So doing that calculation, X plus Y over 4 equals 2. That must mean Y over 4 equals 1. So Y equals 4. So you have now worked out CXHY will be C1, which you don't write in, so it'll just be CH4. And that is how you do that. It's a long process, and it takes a bit of practice, but it's just about taking your time, picking out the facts, and trying to imagine the process in your head. Finally, looking at example 3 then. If we look at example 3, 100 centimeters cubed of an unknown gaseous hydrocarbon, CXHY, were mixed with excess oxygen and a spark was applied. Simply a combustion reaction. A contraction in volume of 200 centimeters cubed was recorded as the mixture was cooled to room temperature. The mixture was treated with sodium hydroxide solution, and a further contraction of volume of 200 centimeters cubed was recorded. Determine the formula of the hydrocarbon. And you can see the first thing I've done here is I've written down the general equation. And remember, that was in the last question, which was very similar to this. So this is the general equation you've got to learn here and use, and it will make your life a lot easier. Let's pick out the information then we need from the question. We've been told that we have 100 centimeters cubed of an unknown gaseous hydrocarbon. So write that in under the equation. We've then been told that we've got excess oxygen, so that tells us that's a useless number. We don't even need it. So bypass that and go straight on. A contraction in volume, so a reduction in volume of 200 centimeters cubed was recorded after the mixture was cooled to room temperature. This should be sparking a light bulb in your head that water's there, the water vapor has condensed at room temperature, and it's told you the volume that it used to be. So in this experiment, there was 200 centimeters cubed of water vapor. So you can put 200 underwater there. And then we're told the mixture was treated with sodium hydroxide solution, and a further contraction of volume of 200 centimeters cubed was recorded. And again, as always, carbon dioxide is the acidic gas here. That's what reacts with the sodium hydroxide. So there was 200 centimeters cubed of carbon dioxide. From that, then you want to work out your ratio. Remember, do that by dividing through by your smallest number, and the smallest number here is 100. So we end up with 1, 2, 2. That's an imaginary 1 in front of CXHY. It's the number 2 in front of CO2 instead of X. So we can now state that X equals 2. Then looking at the last one, water, Y over 2 H2O. Instead of it being Y over 2, it will now be 2 H2O. So Y over 2 equals 2. Work out that algebra, Y equals 4. So your final answer, determine the formula of the hydrocarbon, is C2H4. And that's your 3 examples then that we use here. What I want you to do is actually spend time today getting that into your head. Now, what I've done is I have attached 2 more videos. Now, normally we would only have a single period today, so I'm attaching a few more videos that I want you to work through. If you're still confused, I want you to spend time researching that. If you look up on the internet, the website Chem Guide, it's very good at explaining. You might have the textbook. You might want to look up a fact file. I want you to spend time studying this topic today, because on Friday, what you will be doing is you will be doing the practice questions based on all that we have done so far this week. Okay? If you spend time studying this and you're sitting Friday and you're doing questions about this and you're still struggling, then get in touch. But I want you to really take your time and kind of mentally digest this today. Okay? All the best. Chat soon.